everyone, welcome to this explainer. We're diving straight into a massive transformation happening in engineering right now. It is absolutely incredible to see how artificial intelligence and neural operators are completely revolutionizing computational fluid dynamics. We are literally watching the industry move from incredibly tedious manual simulation setups straight into a brand new era of autonomous, self-correcting workflows.
Here's our roadmap for today. We'll start with the aerodynamics bottleneck, then cover the rise of neural operators, meet the CFD bot agents, look at RAG-enabled error correction, explore hybrid CFD ML frameworks, and wrap up with a future of simulation.
All right, section 1, the aerodynamics bottleneck.
You know, computational aerodynamics has a pretty rich history. A lot of the groundbreaking math we still use today was actually laid down back in the 1960s at Los Alamos. Then, by the 80s, the focus really shifted toward increasing simulation fidelity. Fast forward to today, and supercomputers are routinely chewing through massive simulations with over 100 million grid points. But here's the catch. We've relied almost entirely on hardware speedups to get here. And frankly, hardware acceleration alone just isn't enough anymore to keep up with the demands of rapid aerospace design cycles. We all know traditional CFD is notoriously labor-intensive. It can easily take a senior expert a full week or more just to go from a CAD model to a usable mesh, and then you're hit with endless trial and error debugging. But this new data-driven machine learning approach completely changes the paradigm. It automates the setup, drastically accelerates compute times, and, maybe most impressively, auto-corrects runtime errors on the fly. It totally frees up your senior experts to actually innovate rather than just babysitting a solver.
Moving on to section 2, the rise of neural operators. Now, it's crucial to understand that we aren't just blindly throwing raw data at an AI here. There are two heavy hitters making this work. First, we have physics-informed neural networks, or PINs. With these, we're embedding the actual Navier-Stokes and energy conservation equations right into the network's loss function, evaluating exact derivatives. Meanwhile, Fourier neural operators, or FNOs, take physical inputs and lift them to higher dimensional representations to rapidly solve complex spatial problems. So we are deeply grounding these neural networks in actual physical conservation laws. So how do we actually pull this off? We use a highly effective modular architecture known as the encode, process, decode paradigm. Step 1, we gather our physical variables. Step 2 is the encoder, which transforms that data into a higher dimensional latent space. Step 3 uses a shared latent processor to iteratively solve the dynamics. And finally, step 4 is the decoder, extracting those final predicted physical variables. This modular, step-by-step approach is exactly what allows us to scale multitask learning across wildly diverse physical domains. This setup creates a really beautiful separation of concerns. The encoder module tackles the highly complex, irregular geometries, think airfoils or tricky pipe bends. Then, the decoder takes that process latent data and cleanly translates it back into the physical space to give us actionable fluid dynamics predictions. It's just a remarkably elegant way to handle massive computational complexity. Okay, section 3, meet the CFD bot agents. In a real-world engineering environment, it's wild to see how physical flow descriptions, like case specs and fluid properties, are automatically translated into numerical constraints before grid generation even starts. You've got multiple AI agents talking to each other, passing JSON payloads, configuring OpenFOAM solvers, and writing syntactically perfect C++ dictionaries, all without a human ever touching a keyboard. It really helps to think of these agents like actual human team members. You have a pre-processing agent acting as your mesh strategist, calculating critical numbers like the Reynolds number. The OpenFOAM config agent is basically your C++ compiler, perfectly setting up boundary fields. You even have a debugging engineer actively watching the run and a post-processing agent acting as a validation reporter to extract vital metrics like lift and drag coefficients. Section 4, RAG-enabled error correction. Look, anyone who has run CFD knows the unique, absolute agony of checking on a simulation after 10 hours only to find out it crashed at hour 2, right? Well, when a 3D simulation diverges or hits unphysical limits, this agent acts as a real-time debugging engineer. It intercepts the crash immediately, diagnosing the issue before it wastes days of valuable supercomputer time. Here's how it does it. First, the agent scans the standard output logs in real time looking for crash triggers. For instance, a current number blowing past 1.
Next, it queries a highly specialized RAG vector database that's just filled with OpenFOAM source code errors, trouble tickets, and stability guidelines. Finally, it automatically generates and applies a precise code patch, like lowering the time step, and reruns the solver, completely autonomously.
Which brings us to Section 5, Hybrid CFD ML Frameworks. The industry is actively shifting toward these hybrid frameworks. During preprocessing, convolutional autoencoders are used to predict optimal local mesh refinement boundaries. In the solving phase, deep neural networks are trained on fine mesh data to generate coarse mesh closure relations, which accelerates the math while totally preserving the physics. And then in post-processing, GANs automatically identify and render incredibly complex 3D vortex structures from massive datasets.
There's a ton of hype out there claiming AI is going to instantly replace all traditional physics simulations. But honestly, that's just not what the data shows. AI is not here to replace fundamental Navier-Stokes numerical solvers. It's here to augment them. Machine learning is being applied to accelerate those specific, tedious phases of the workflow and completely remove the bottlenecks that hold engineers back.
Finally, Section 6, the future of simulation. So here's the ultimate question we have to ask ourselves. When autonomous agents, neural operators, and RAG databases handle all that mind-numbing trial and error of setup and debugging, what happens next? Your senior aerodynamicists are finally freed from babysitting computer codes. They can focus purely on true innovation and pushing the boundaries of what is physically possible. Thanks so much for joining me for this explainer. I really hope it sparks some ideas for how you can revolutionize your own workflows.